Welcome! Today, we are going to explore the binary search tree, or BST. However, we will not just look at it as an abstract diagram of circles and lines. We will deconstruct it as a physical entity living in your computer's memory. We will see how a simple logical rule, the search invariant, dictates everything from algorithmic speed to the behavior of your CPU's cache. Let's begin with the theoretical framework. At the bedrock of this data structure lies a single, non-negotiable rule known as the search invariant. This is the invariant. Mathematically, it states that keys in the left subtree are less than or equal to the root, and keys in the right are greater. However, this formula creates ambiguity regarding duplicate values. To ensure the tree behaves deterministically during insertion and search, real-world implementations must enforce a strict tie-breaking rule, such as always sending duplicate values to the left. This logic is implemented recursively. As you see in this C++ snippet, a node contains its data plus pointers to its left and right children. But be careful, recursion relies on the system call stack. If a tree becomes too deep, imagine a straight line of 100,000 nodes, you risk a stack overflow error because the operating system runs out of memory to track the recursion depth. We perform three main actions on this structure. First is search, which traces a path from root to target. Second is insertion, which also traces a path but always attaches the new data as a leaf node. Third is deletion, which is the most complex. If you remove a node that has two children, you cannot just leave a hole. You must find a replacement, usually the immediate successor, to fill the gap and preserve the sort order. Now, let's talk about performance. In theory, binary search trees are incredibly fast, but in practice, they suffer from a fatal flaw related to geometry. The promise of the BST is logarithmic time complexity. If the tree is balanced, its height grows very slowly. For example, in a balanced tree containing 1 million items, finding a specific record takes only about 20 comparisons. This efficiency is why trees are superior to simple lists for large datasets. However, the standard BST does not guarantee balance. Its shape depends entirely on the input order. If you insert data randomly, the tree stays relatively bushy and fast. But if you insert data that is already sorted, like 1, 2, 3, 4, the tree degenerates into a long, thin linked list. Your lightning-fast logarithmic search crashes down to linear speed, checking every single node one by one. This is where we leave the textbook theory and look at the silicon. How does a BST actually behave inside your computer's RAM? The reality involves pointers, padding, and cache lines. Tree structures are surprisingly expensive in terms of space. On a modern 64-bit system, storing a tiny 4-byte integer requires two massive 8-byte pointers plus 4 bytes of padding for memory alignment. As this chart shows, over 80% of your memory is consumed just by the structure itself, not the data. This reduces the density of information in the CPU cache. There is also the cost of movement. In an array, data sits side by side, so the CPU can predict and fetch it easily. In a BST, nodes are scattered randomly across the memory heap. Moving from a parent to a child requires pointer chasing, jumping to a random memory address. This prevents the hardware prefetcher from helping you, leading to frequent CPU stalls while waiting for data to load. Furthermore, modern CPUs try to speed things up by guessing the outcome of if statements before they happen. In a binary search, we compare the target value against the current node's key. The result, going left or right, is effectively a coin toss on random data. The CPU frequently guesses wrong, forcing it to flush its execution pipeline and start over. For small datasets, a simple array scan is often faster than a BST for exactly this reason. To solve the problem of geometric degeneracy, computer scientists developed self-balancing trees. These structures enforce strict rules to ensure the tree never becomes a line. The two titans of self-balancing trees are AVL and red-black. AVL trees are strictly balanced. They keep the height minimal, making them perfect for databases that are read often. Red-black trees are more relaxed. While they also use rotations to maintain structure, they primarily rely on computationally cheap color flips to fix imbalances, reserving complex rotations for specific cases. This makes red-black trees faster for general-purpose writing. Finally, we have specialized variants for specific hardware problems. B trees group many keys into a single massive node to match the size of a disk block, drastically reducing memory jumps. Treaps use randomness to avoid worst-case scenarios without complex rules. And splay trees move frequently accessed data to the top, acting like a self-organizing cache. In conclusion, to master data structures, you must understand both the math and the machine. The standard BST is elegant but raw. By understanding its physical limitations, pointer overhead, and cache misses, we can appreciate why modern systems rely on robust engineering marvels like red-black and B trees.